Hello, my name is Jack Langerman, and I'm going to talk about metrics for measuring the quality of structured 3D reconstructions. This is joint work with Rozumnyi, Yuzhong Huang, and Dmytro Mishkin, and it has been accepted as a highlight paper at ICCV 2025. So what do we mean when we say structured 3D reconstruction? Take, for example, the problem of extracting measurements of a house from a collection of images. We want to extract some representation from the images such that we can easily and automatically read off the measurements we care about. We call this representation a structured 3D representation or structured 3D reconstruction. Concretely, for this work, we consider graphs embedded in 3D space or sparse wireframes as our structured representation. But of course, this begs the question. There are many ways we could produce such a representation. Given two reconstructed wireframes of the same scene, how should we quantify which is better? In addition to these properties, we collect a set of expert quality judgments given pairs of reconstructions corresponding to the same ground truth. So where did we get these wireframe reconstructions? Well, we collect a set of real-world reconstructions from the aforementioned S2-3DR challenge at CVPR 2024. These were submitted by participants and judged against ground truths that have undergone significant validation, which were created by human experts. In addition to the real-world samples sourced from the aforementioned challenge, we include a set of synthetically generated wireframes created by corrupting the ground truth. Here, we remove some edges in A, and then remove additional edges in B. We should all agree that A is closer to the ground truth than B is. This is the motivation for introducing the second pool of wireframes. We want to include unambiguous pairs that allow us to rank the raters, both the humans and the automated metrics. This allows us to create quizzes to check rater ability or reliability. We use these quizzes to qualify raters. Our expert pool achieves 98% accuracy on these quizzes. Recall, our goal is to find metrics that agree with these human expert judgments. We recruit a group of 17 raters from 3 subgroups. Expert 3D modelers from the same group who created our ground truths, computer vision and machine learning engineers, and designers. We ask all raters to rank all pairs from both pools for a total of a little over 3,500 pairs. So, do humans agree with themselves? Are they self-consistent? Yes. When showing the same pairs repeatedly, humans pick the same winner about 90% of the time. Similarly, do humans agree with each other? Well, under certain circumstances, excluding ties and within clusters, raters also agree with each other around 90% of the time. So let's make clear what we mean by metric and how we use these metrics to rank pairs. Given some metric D, along with a ground truth wireframe and 2 reconstructions, A and B, our metric D tells us how close each reconstruction is to the ground truth, and the closer reconstruction is the winner. We use several methods to quantify the degree of agreement and extract the underlying rankings based on the pairwise preferences. We start with the empirical win rate. For each pair, we compute the average win rate taken over all raters, and then compute the global win rate averaging over all pairs a given method participated in. We also estimate latent abilities for each reconstruction method via a Bradley-Terry model. We estimate the probability that method I beats method J as the sigmoid of the difference between their abilities. We initialize these abilities randomly and then update them by minimizing a binary cross-entropy loss between the predicted probability and the label assigned by the community of human raters. Finally, we take a factor analysis-based approach and estimate a single quality factor which describes the rater's judgments by taking a rank 1 factorization of the empirical log odds matrix formed by observing the proportion of the time each rater chose each method as the winner when it appeared in a pair. So why do we use so many different ways to determine rankings? Using different and varied methods to extract the pseudo-ground truth ranking of the methods from expert pairwise judgments allows us to verify that their judgments are stable and meaningful. We check the correlation between the different scoring methods, Bradley-Terry and SVD, and find a Kendall correlation coefficient greater than 0.7 between the rankings implied by SVD and by Bradley-Terry. This lends additional evidence to the hypothesis that there is a true underlying quality factor driving the rater's views. This is observation 4.6 in our paper. Given stable rankings we are confident in derived from the expert human judgments, we compare the rankings implied by a number of handcrafted metrics to those given by humans. Here, we list several families of metrics we considered, each of which have several subvariants. Please check our paper for details and definitions of each. Additionally, we distill the human preferences into a learned metric via transfer learning. Given a pair of 3D wireframe reconstructions I and J, we render each from a canonical pose along with the corresponding ground truth to create a pair of 2D images. We then feed each rendering into a frozen Dino V2 backbone and then extract a score via a shared MLP. Adopting a Bradley-Terry formulation, we model the probability that reconstruction I is better than reconstruction J as the sigmoid of the difference between the predicted scores from the MLP, which we train by minimizing a binary cross-entropy loss using the human preferences as labels. Averaging over a 10-fold cross-validation split, we observe 76% prediction accuracy with respect to the human labels. Finally, we show a selection of metrics along with their average agreement to the human raters. Our learned metric shows strong agreement with expert judgments, and we find that humans care more about recall than precision, both for edges and vertices. However, recall-only metrics and neural networks are hackable. In environments subject to aggressive optimization, such as in RL environments, when gradients are available and when there are cache prizes, we recommend using the harmonic mean of the vertex F1 score and cylinderized edge IOU, which we denote the hybrid structure score. Read our paper on arXiv for additional details. The code and data to reproduce all of our experiments are available on GitHub, and you can also check the ICCV poster page and come see us at the conference. You can also feel free to ask us questions on social media or via email. Thank you for your interest in our work.